And this is what we'll use here.
That is what you use, okay. Thank you. Well, everyone, welcome, thanks for coming. As I said, I've been in the industry for a few years, been in this building for a few years, so got a little experience. I don't tend to be a professor, but I can hopefully answer a few basic questions for you. But the first thing I'm going to go over is the glossary of terms, just because we do kind of speak a unique language. If you just kind of off the street and start listening to us, the conversations, but like going to Paris with the Olympics, you don't understand half what's being said or don't know all the terms behind it. So we're going to give a little bit of a glossary and some of the definitions.
You may hear us
I got
talk
it.
about some of
have it.
this.
This is what we need, sorry.
Thank you. Doug, what did you say? I'm sorry.
I was just saying, you may hear us talk about some of these and a good one is air turnover or ATO. So now if you're in hear a conversation or you're involved in a conversation, you can at least go back to this list and say, what the heck are they talking about?
Exactly. So an air turnover unit designed typically set in a space, typically indoors. We do make a few of them outdoor models, but it's a low level return, high level discharge. We bring air in at the floor level, we condition it, whether it's heating, cooling, filtration, whatever, discharge it up above the work level. And that constantly rotates. And by moving that air around, we eliminate, or not eliminate, but we reduce stratification. So it used to be a floor ceiling difference of 25, 30 degrees because hot air rises. We get it down to 3 to 5 degrees by using air turnover. So it's more comfortable throughout the whole space and it saves energy.
And it continuously runs.
Yes,
So
the
that
fan,
unit stays on all the time.
the fans run continuously. Thank you, Doug. The burner cycle as needed for the heat or cooling that may be, but the fans will run all the time to keep that air moving. Again, keep the stratification down. A blower, that's just any term or vehicle that we use to move air. Might be a prop, it might be a centrifugal blower. We kind of use it as a loose term, but it moves the air in the system. A BTU, we always talk about, what's a BTU? That's how we measure heat. And it's just the quantity, it's the temperature. 1 pound of water, 1 degree Fahrenheit. That's what 1 BTU is. And to give you an example of what that might mean on a cooling side, 10 unit in their house or 5-ton unit. 1 ton of cooling is 12,000 BTU. So you can kind of relate to what that might be there. H is BTUs per hour. That's how it's rated as an hourly rating. The building load, that's calculations we do to determine the complete load in the building, whether cooling or heating. That takes in many factors we'll talk about a little bit later, but the complete building load, walls, people, infiltration, all of those things play into it. CFM, cubic feet per minute. That's how much air we typically move. That's a volume of air. So that's not speed or anything, that's a volume that we're talking about. Chiller. We start talking about cooling units. We basically make 2 types of cooling units that we get into. And we don't make these. These are an outside source that other people supply. But if you have a chilled water system, someone in the area, on the campus, whatever, has a chiller that cools the water down to a low temperature and pumps it throughout a complete system. The condensing unit, on the other hand, is you have a refrigeration system. So if you have your home, apartment, whatever, you've got a condensing unit outside where it rejects the heat. That's a condensing unit for a refrigeration system. Cooling CFM per ton. This isn't a term per se, but it's just one of those formulas that we throw out like everybody knows it. The rule of thumb is 400 CFM per ton. And if you have someone come to your house and want to help size an air conditioner, give you a quote for one, they look at the grills and they know exactly what that grill's rated for CFM. Add all that up. Oh yeah, you need a 3-ton unit. They know that based on the CFM that you're moving to the building. The cooling coil, that's a coil arrangement with pipe and tubing, and it's got fins on there that transfers the heat of any two fluids, and it's chilled water, refrigerant, and then it transfers the heat from the airflow to the coil. And if it's hot water, it goes the other way. It goes from the coil to the airstream. But it's a cooling coil is one term of a heat exchanger. It transfers heat. Cooling coil velocity, another thing we just throw out among ourselves, like everybody knows this. Well, there's a sweet spot on the coil when you get the best performance. And for DX, direct expansion refrigerant, or chilled water, that is between 450 and 550. Most of our coils are sized around 500 feet per minute as our sweet spot. And that's just because we know if you get velocity too high over that, on a cool, you're going to get water out of the air when you cool it down. Well, if it's higher than 500, you have the possibility duct work or potentially into the building. You don't want that in the unit. So we keep the velocity around 500 and water get in the airstream with that velocity. If you go too low, you don't get enough heat transfer across the coil. So you have to kind of, again, have that sweet spot. We like to go around 500. DB means dry bulb, and we'll hit that description later. So, but just as an abbreviation for dry bulb. Delta T, that's a temperature difference. You know, if my delta T for my building between inside and outside 70, that means the outside temperature is 70 or outside temperature is 0. I want to hold 70 inside. So that difference is a delta T. And it's often written in formulas used as it shows the delta and then the T for the temperature difference. Direct evap cooling. If you've been around or in the shop, you might see us building some Alton evap units. Those are direct evaporative cooling. What that means, the air is cooled by drawing through either a curtain of water or the media. We use the media and is direct contact with water. Water is involved and touches the airstream. That's how we cool it. That's a direct evaporative cooling. It will have humidity of the airstream. We're doing a run through on level 2, and you can see what that does to your temperature. But great systems, and they're very efficient as far as cost-wise, but there's drawbacks too. You have to be aware of what you're getting or not getting. A direct gas-fired heater. What that means is the burner is directly in the airstream. There's no heat exchanger. So as the air comes in the rear of the unit, there's an open flame that the air goes over. We'll heat up that airstream, and then it's blown out into space. So there's no heat exchanger, thus no flue or stack to worry about, and 100% of available BTUs are delivered to the airstream. The drawback is you're putting the products of combustion in the airstream. But we'll show you again in version 2 the levels we have to maintain on direct fired units. They're a very safe system. They're mainly used for makeup air. In other words, they don't get recirculated as a rule. If you have exhaust fans, let's say you're exhausting 20,000 CFM out by your welding booth. We're bringing in 20,000 CFM of fresh air. So if we don't want just bringing in cold untreated air, we go through a direct fire burner to heat it up to, let's call it neutral air. So you're not bringing a cold mass of air in here. So they're very efficient with that. Now, over the last 10 years especially, they've got some standards they've changed, a lot tighter control on how the burners work and the electronic controls we can use. They are used more and more now for space heating. There's limitations. You can't have 100% return, or you can have maybe 80%. You have to have some fresh air coming in. But they are used more and more for space heating as well. Here we go. We mentioned dry bulb before. Abbreviation of dry bulb temperature is the ambient temperature put on a thermometer. It's not a when if you're a weather report or you look out and your thermometer out your window, that's a dry bulb temperature that you're seeing. What we actually feel per se. Duct static pressure, and every time we have a ducted system, and we're pushing air through it, there's resistance there we have to take into account. The smaller the duct, the higher velocity is real high. If you got a big duct, the static pressure is going to be lower, but you're still going to have some. So that's the amount of pressure a fan has to push or pull against to move the air through the system itself. And so anytime there's a duct involved, you're going to have some duct static pressure. EAT, abbreviation, we see a lot of them, specs or formulas, whatever. That means entering air temperature. ESP is internal static pressure. And what that means to us is anything external to our unit. But we have to take into account that everyone kind of looks at this different. Some of the engineers we talk to in the lab unit, if we put filters on there, they consider that external to the base unit. The other abbreviation we throw around EWT. That is entering water temperature. That might be what we have in there if there's a chilled water system or even a hot water system. The coil is going to be rated, and you have to take into account the entering water temperature in your formula. Electric heating system, the heat's transferred through a big electric element mounted in the airstream. And the best way to describe these, you look down when you're making breakfast in the morning, you look down at your toaster, you see that grid of electric wires that are glowing red. That's what these are. Electric heating element mounted in your systems is like a toaster on steroids. Great big coil that gets red hot, but if air goes through it, we have some heat transfer, so we're heating the air. Feet per minute. When we're talking about, I threw this number out already when we talked about the sweet spot coil, talked about feet per minute flow. That is the measure of speed. CFM was quantity, feet per minute is speed. So that's how fast the air is moving. Handing, this is a tough one. It's not a term per se, but I just wanted to bring it up so everyone realizes that not everyone in the world looks at this the same. We look at a unit, and on this particular plant, if you're facing the direction of the airflow, and the air is hitting you in the back of the head, so you're in front of the unit, the air is hitting you in the back of the head, controls are on the right, that's a right-hand unit. I'm going to say most manufacturers look at it that way too. But one of our vendors that we deal with, and Doug can swear to this one, Train, they look at it but opposite. They're looking at the air hitting them in the face. Right-hand units are controls on the right. So their right-hand unit is left-hand to us. So whenever they order a right-hand coil, we have to make sure we understand our language versus their language. Right. So that's the reason I throw that up. I mean, it just means the side of the controls wrong, but be aware, some people look at it different than we do. I do think 80% of the people look at it as we are.
Yeah, most manufacturers and most people in the industry look at it the way we do, unless you work for Train.
So, where did that come from? Is that a European style or what?
That's a good question. It's kind of, I don't know, I think some manufacturers throw something in there to be different. Linux, for instance, on residential equipment. Train is on that part. Train.
They want to be unique. They want to be unique. Don't confuse them.
All right, so now after that, we get into heater efficiency. If we have a heater on there, the heater efficiency is the percentage of BTU input that's realized as useful BTU output of the heater. So, as I said, on the direct fire, all of the heat goes into the buildings. On an indirect fire, you've got a stack, so you're exhausting part of it outside. Our typical units are 80% efficient. So if you've got 1,000,000 BTU input going in, you're only going to get 100,000 output. The rest goes out to the stack and outside. So that's how we figure heater efficiency is what you have going in and what you're taking advantage of as far as the output. HLO is another abbreviation we use, meaning high low off. That tells us on our burners, it's a two-stage burner. It's high, it's low, or it's off. Two-stage burner, high low off. A hydronic heating system, that's again a coil arrangement in pipe and tubing, water or steam, mounted in the airstream transfer. Again, that's another version of a heat exchanger. You've got water and the air, water in the tubes, and the air going across the fins, transfers the heat. You've got a heat exchanger there. Inches of water column. That's the way we measure the resistance to the airflow in a duct system or across the component. Is a damper, for example. We throw out just a standard number that if you've got an on-off damper, we've got 0.13 inches of water column pressure drop. That's what we base that on. Filters might be a 1/4 inch. That's typically a dirty filter reading, but that inches of water is how we measure the resistance we have in that ductwork or the component.
And that's used in pumps, coils. You'll see that's used in measuring resistance in a lot of applications.
That's correct. Thank you. We're going to talk a couple pages back about directing back cooling. Indirected back cooling is another way to go about this. And if you see any of the Aztec units going through the shop, that's what they are known for, is indirect. In that particular one, we use a secondary heat exchanger as a cooling tower, and that lowers the water temperature because you run it through this media and it drops it down to wet bulb temperature. And then that's pumped through a coil, and then that coil then acts like a chilled water coil to lower the temperature. So we lower the temperature without having water in contact with the airstream. That's why it's indirect. Water's not in contact with the air. And that particular one, we can lower both the dry bulb and the wet bulb without the cost of refrigeration equipment. Actually, that's a little, you don't have the cost of refrigeration, although the MACE unit is not that much cheaper, but operating cost is about 20 cents on the dollar for the refrigeration system.
Yeah.
So big operating cost difference. Now they also get into an indirect direct. We do an indirect evap cooling, drop it down quite a ways, and then we can put in direct evaporative cooling after that and lower it a few more degrees. Again, on level 2, we go through an example. We can show you what the temperature can be and what that can get down to without putting refrigeration systems in it. Indirect fired, gas-fired heaters. Now we have those in a stainless steel heat exchanger or some sort of a combustion chamber. And that's what we pass the air over, and then that heats the air. So this is another version of a heat exchanger, transferring heat. Then the combustion gases are exhausted through a flue system and outside the conditioned space. You don't want them being put back in because you do have CO and some bad stuff in there you don't want to be breathing. KW is a term you use, and you probably might see that in some of the things. It stands for kilowatt. That equals 1,000 watts. So you think of something that you relate to a 60-watt bulb. If you have a 1,000-watt bulb, that'd be a kilowatt. That's equal to 3,412 BTU. So that's how many BTU you can get heat transfer out of the KW. LAT is leaving air temperature. We have EAT up front for entering. Leaving is LAT. And again, to pound that home, LAT minus EAT is delta T. Like before, we had entering water temperature. LWT means leaving water temperature. So again, if they're rigging a coil, of either heating or cooling, you will have an entering water and a leaving water that you have to take into consideration. That will help determine the coil capacity. Latent cooling load, and this is just what you had mentioned. What that is the amount of moisture added to the inside air by plants, people, cooking, infiltration. People have a great amount of latent heat. We talk about this group in here, we're producing some latent heat in this space just because of the people we have. But in a resident, you have to take into account the people, how much cooking they do, boiling, whatever, all those take into account. If your windows and doors leak, you got infiltration that's coming in from outside. That's all going to be some latent cooling load. Latent heat now, what that is, that's the process of changing the form of the substance. So if you have water and it goes to steam, we change the state of it. And there's a big change in BTU between hot water and steam. On the other extreme, you get on 32 degrees, there's a change of state between water and ice. Again, that's a latent heat we have to take to get to that step. And those are some pretty significant numbers that we'll talk about in more detail later. But latent heat is a big factor we need to take into account, especially on the cooling side, obviously. We learn it from heating as well, but make up air equipment. We kind of talked about that before with direct fire. It's designed to draw sufficient outside air into a building to wholly or partially offset the amount of air that leaves the building through its, whether it's exhaust fans, just exfiltration for whatever reason it might be. And it may or may not be tempered or filtered before it being introduced to the building. Well, we like to have a makeup air unit that tempers the air and hopefully filters it too. So we're bringing in clean, again, I use the term neutral air into the space, what we try to do. And that, my neutral air, that can be either cooling or heating application, depending on what they're trying to do and how important it might be for their operation. MBH means 1,000 BTU. That's what that stands for. MERV, M-E-R-V, another abbreviation we throw around, that's a filter rating. And basically, just be aware that the higher the rating, the higher the filtration capability. That's the good news. Higher the MERV rating, the higher the filtration, the higher the duct static pressure it's going to have. You have to work harder to push the air through that. So there's a drawback to everything,
Filters are tested nationally to a MERV standard.
Yes. So you might want the better filter, which is going to have more pressure drop, which may affect your airflow. You need to take that into account. Airflow and or horsepower to move it. This is the number we throw around. We're talking about combustion. That means parts per million. So as a rule, they're relatively small numbers, but we have to test a certain standard. We have to hold these numbers. Volumetric chart. That's a graph that we can show that presents the physical and thermal properties of moist air in this graphical form. Again, if you're going to be in level 2 later on, we will show a psychometric chart and the very basics of how to use it, what it can do for us. A prop, that is a term or just abbreviation that we use for propeller fan. Like you go outside in your home and see a condensing unit where your compressor is, you've probably got a prop fan on top of exhausting that air. It's a very easy way to move air, large volumes as a rule, but they don't work with high static pressure. They're a low static pressure application, seldom used with ducted systems because they do have limitations. You put just a little bit of static on those drop fans and you can drop 25% of your capacity off like that. They just aren't made to work against that much static. R value, that's a rating system used to grade insulation products or the system itself. So you got an R value in your insulation on the ceiling and your walls, whatever it might be. Even the windows have an R value rating. So that's just a value that we can look at and compare with how well that's insulated. And when you do a heating and cooling load calculation, you have to know that number so you can estimate the heat loss or heat gain through walls, windows, whatever it might be.
It's the resistance. If it's 100 degrees today outside, it's how long it takes. What's the resistance? How long does it take for that heat to get through the walls and into your house or your building?
RH, we hear that abbreviation relative humidity, and we hear that, oh, I guess I skipped over humidity, I'm sorry. Back up to that one. Ratio of the amount of water vapor present in the air compared to the greatest amount that same temperature can hold. So if your relative humidity is 50%, they give you that on the weather. That means it's only holding 50% of what is capable of holding at that temperature. And then the RH is just the abbreviation relative humidity. So that's what you typically hear on a weather report. You know,
The human body's most comfortable at about 45 to 50 degrees of relative humidity. So if you listen to a weather report or you look at it on your phone, and it'll give you the relative humidity at that temperature, you can determine what's going to be a muggy day.
Yeah, but we all know the difference between a 100-degree day in Houston and what a 100-degree day in Phoenix would be.
Exactly.
Yeah.
A big difference. So sensible heat, that's the heat that causes the change in temperature but not in state.
So where does it need to be, right? Okay.
So I talked about latent heat earlier, that changes state of the, water to steam or water to ice. That's a latent, but sensible heat, 80 to 85. That's a sensible temperature change. Stack loss. This kind of goes hand in hand with what we had earlier, what the heater efficiency is. I told you that most of the furnaces here in this plant are kind of 80% efficient. Well, that means that 20% goes out stack. Because they're 80% efficient, the other 20% we lose. That represents the heat that goes out of the stack on an indirect fired heater. Stratification is the basic layering effect that allows large pockets of different core temperature to remain intact. And that's just influenced the buoyancy of air. And we all know that hot air rises. And so, like in a typical building, I know, for example, the one across the street, we have a heater in there. They put heat in that space on, be that direct fired unit on the side. And they keep the space warm. It might be 65 degrees at the floor level the workers are, but it's like 100 degrees at the ceiling. I know from experience that they go over there about 30 feet away and turn on that air turnover unit. No cooling on it. They just get the air moving. Talk about air turnover, get rid of stratification. Within 30 minutes, the floor to ceiling temperature in that building was 5 degrees. All that weight, that temperature up there is wasted.
Yeah.
Back down to the floor level, we're still using that. So it cuts the heating bill down. Everybody's more comfortable. In some cases, like pharmaceutical warehouse, they can't have a stratification. They have to have even temperature throughout. So it helps the product in some cases as well, but creature comfort, products, whatever it might be, besides energy efficient.
It's the temperature differential from floor to ceiling, the stratification.
That's right. Temperature rise, that's the amount of temperature difference as supply air passes over a heat source. Again, can also be known as delta T. I threw this number out earlier, a ton of refrigeration. Refrigeration effect equals the melting of 1 ton of ice in 24 hours. That's where a ton of refrigeration cooling came into being. Expressed as follows: 288,000 BTU divided by 24 hours, 12,000 BTU per hour. That's a ton of cooling. So if you've got a 5-ton unit out to residential, it's a 60-ton, or I mean 60,000 CF or BTU. Well, that would be out to. Now take that into account. Some of the, I think the unit upstairs at one point was a 60-ton unit.
Yeah.
That's 360,000 BTU of cooling that we could supply. So
Yeah.
the total heat, and again, I talked about when you get into cooling, latent load is big. So total heat is the sum of both sensible and latent heat load.
But add those two together.
Yes. If you look at the performance of a coil, at a coil run, get your performance that give sensible, latent, and total load based on BTUs. That would be the sum of the duct static and our accessories we add. So in other words, they might have filters, might have a damper, they might have some other special component in there, or all you throw in, come on out an air blender maybe. All those are external of our unit, and they aren't in the ductwork per se. So that's plus the duct static on top of that. So those add up to total external, everything over and above our working unit. A watt, we talked about what a kilowatt is. Well, a watt is just electricity. It's volts times amps. That's what a watt is. And then again, remember, kW is 1,000. WB is abbreviation for wet bulb. Let's jump down to this one. Wet bulb temperature is the lowest temperature that air can be cooled to by evaporation of water. So, and that's going to be a relationship to relative humidity. We'll show you that later on. Another thing, the higher the relative humidity, the higher the wet bulb temperature. They kind of run in conjunction. WC is water column. I talked about inches of water column when we measure it. Well, that's what this is, water column measure of air pressure in duct systems. Wet bulb depression. We get into that when we start talking evaporative cooling. That's the difference between the dry bulb and the wet bulb. So, and we need both of those numbers so we can figure out what an evap unit will do at the leaving air temperature.
Wet bulb, when you're looking at the weather report, if the air temperature and the wet bulb temperature get close to the same, it's gonna rain. It can rain inside a building.
You don't have that problem.
Yeah.
Or you'll have a heavy dew or a foggy condition. That's when your wet bulb.
Actual temperature.
So I know we ran through those fast. We wanted you, and again, you got the handouts to keep, and you can kind of look back on it and throw these weird terms out. But wanted to throw that out so you can see it. Any questions on that material before we move on? And then a break, we get the computer changed out, or is anyone ready for a break? Or
Is anyone ready for a break, or do you want to push it through? We got another
Mm.
hour and a half.
It won't even be that long,
We got the presentation part.
and that's not that
This is
long.
just the glossary of terms, things that you'll hear everybody in this building talk about from time to time. Now you won't be lost.
Changing.
No, we're gonna just keep- no, just do one glossary. Let me, yes.
Check in here.
Now I know.
Anybody need water? I can go grab some. You're not doing the presentation.